All right, so section 1.1. So this is Unit 1, Section 1, and it's called Exploring Real Numbers. So a lot of this is going to be just really about definitions of things, but a lot of these definitions are very important to know to kind of have a foundation to start off with. We're literally starting off the entire course here with this lesson, exploring real numbers. And you might have just kind of quickly glanced over or heard me say this title, but the word real right here is very deliberate. So all of these numbers are actually labeled as real numbers, as opposed to, well, one day, so spoiler alert, one day, not even in this class probably, but you'll be learning about imaginary numbers. So every group of numbers that we define here in review, they are all under the umbrella of real numbers. So let's start off with the natural numbers. The group of natural numbers is often called the counting numbers because we use them when we count. So all of these, starting with 1 and then 2 and then 3 and then 4 and then 5, on and on and on and on and on, just keeps going and going. This is the group, this is the set of natural numbers. These are the natural numbers. And just kind of say this once and then just kind of get on with the video and never have to repeat it again. I might go a little bit faster than you can write, but if you're watching this video, I assume you have the ability to pause it whenever you need. If I start to go a little too fast, for how quickly you can copy down these notes. So copying down this set of natural numbers, okay? So obviously you can pause the video as needed. Heck, you can even speed it up, I'm sure. The playback speed or whatever on YouTube or whatever you're watching this on, probably YouTube. So next is the whole numbers. The whole numbers are actually like pretty much the same set as the natural numbers, but we're also tossing in 0. So the set of whole numbers is basically 0, 1, 2, 3, 4, 5, yada, 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 forever and ever and ever. Okay? Next is the integers. So what are the integers? What's the set of numbers that we call integers? Well, one way to write it down here in your notes is just like this, where we can kind of go in the positive direction with 0, 1, 2, well, actually 0 is not positive, but anyway, 1, 2, 3, dot, 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 but also -1, -2, -3, and so on and so forth in the negative direction. So the integers is essentially all of the whole numbers and their opposites. Spoiler about the word opposites. We might even officially go over that vocabulary word later on in this very video, maybe, if I remember correctly. So all the whole numbers and their opposites. So integers are still pretty nice numbers, just including negatives. Then we get into the whole world of rational numbers. So you might think of rational numbers with a certain definition, but here we're going to start off by thinking of them as any number. So the whole set of rational numbers, okay, is any number that can be written as a quotient of two integers. In other words, a fraction. So we'll get into the other sort of way to define or know what a rational number is in a minute, but the textbook definition is any number that can be written as an integer or as a fraction. Okay? So all the natural numbers are the natural numbers all included in the rational numbers? Yes. because any natural number like 5 can be written as a fraction. How can you write 5 as a fraction? Like that. You can write 5 or any natural number as 5 over 1. So if a number is natural, it's automatically also included in the rational number set. The whole numbers, yeah, for basically the same reason. So 0, I guess, is the only whole number that's not natural. Can you write 0 as a fraction of two integers? Yeah, it's the same thing. 0 over 1. Are the integers, is every integer also, can you also label it as rational? Yep, because of the same reason, right? Can you write -3 or -4 or any other integer that's not also whole, that's not also natural? Can you write those as a fraction? Yep, same, same justification, same way you can write it as a fraction and put it over 1. All right, now, so again, like I said, that's actually the textbook definition of rational, the ability to write it as a fraction, of two nice integers. But when you first saw the word rational, you might have thought of this sort of unofficial definition. So rational numbers, another way to think of it as, they're basically numbers that have a decimal that either terminates at some point or repeats a never-ending pattern. So not only are natural numbers included, because look, and by the way, can you say that 5 has a terminating or repeating decimal? Yeah, 5 is like 5.0 or 5.000000, I mean, whatever. So yeah, 5 and 0 and -3, these have decimals that can be, described in this way. But when you think of decimals, normally you think of things like 3.82, okay? And this has a decimal that terminates after only 2 decimal places. So yeah, this is included. But again, it also fits the official definition of being able to write it as a fraction, and that's what you would do. If you wanted to prove that you could write it as a fraction, or something like this, this has a terminating decimal because it stops, it terminates after 4 places, and you could write it in the same way. You might start by writing this as a mixed number, like -14 and 6,517 over, 10,000? And then you could kind of change that to an improper fraction. I'm not going to go into it there. All I'm trying to kind of get across here is you can easily also think of rational numbers with this unofficial definition. As long as it has a decimal that terminates at some point, or in a way never really starts, like these natural numbers or whole numbers or integers, you can qualify it as rational. It fits under the rational umbrella. 9.2 you can write as 92 over 10, or like 9 and 2/10, which you could then change to 92/10. But also included is anything that has a repeating decimal. If it repeats a pattern forever, it also fits in the rational set. Because 0.33333333, what fraction is that? 1/3. And this with a repeating, even though it goes on forever, it at least repeats a pattern forever. 1.7272727272. Turns out that, and we're not going to get into that can of worms, but it turns out that this fraction is 19 over 11, would be this 1.72727272 forever. Okay? So again, just there was a lot there. That was a big sort of section of this video, pausing on rational numbers. So again, just to kind of summarize, if you can tell that a number can be written as a fraction, it's rational, or you can look at it and determine whether it's rational by its decimal, whether it terminates at some point or repeats a never-ending pattern. And by the way, numbers like 5 fit in that category. So then we get into like literally the opposite, not to throw around that word willy-nilly, because again, opposite does mean something very specific in mathematics. But irrational is almost like the, converse. I don't want to start throwing wrong words I'm not sure of. So we'll just say opposite. Irrational is like literally the opposite of rational. So any number that's not rational, I suppose, would automatically be irrational. So if a number literally can't be written as a fraction, it's irrational. So what numbers would that be? Okay, like, in other words, if you think of the whole decimal thing, if a number is irrational, wouldn't it then have to have a decimal that not only never terminates, but it would at the same time never repeat a pattern? If you have those two things in play, that number would be irrational because it's not rational. So what kinds of numbers would fit this description? Either this description or this description. Can you think of any number that would have a decimal that not only never ends, ever, but actually just, it almost seems like random decimals forever, and they never repeat a pattern? Do you know examples like that? The square root of 2 is a nice example. Or actually, pi, you might have thought of pi. In fact, chances are, if you're like students I've had over the years, this may have been the first example you thought of. Pi is about 3.14, but again, remember, that goes on forever. 3.14159, that's as far as I can go. But the decimals go on forever, right? And actually, I'll pause right there just to kind of let it sink in that as far as you're concerned here in like Algebra 1, you're most likely a 9th grader or a 10th grader, okay? And you haven't had that many math classes under your belts, right, in your life. This is probably the extent of what you might know about irrational numbers. Square roots and pi. And to a large extent, okay, that's it. That's it for irrational numbers, okay? Not all square roots, mind you, because think of, say, the square root of, I don't know. And I hope I'm not getting too far ahead of you here with talking about square roots of certain kinds, but what about the square root of 16? Is this irrational? Does this have a never-ending, non-repeating decimal? No, because the square root of 16 is just 4. It's like the square root of 16 is very nice. The square root of 2, not very nice. This decimal is crazy. The square root of 8, not very nice. This decimal is crazy. But the square root of 16 is actually rational. This is very rational. This is very irrational. This is very irrational. And let's see what else I have here. Well, another square root, okay? Like there's so many square roots. There's actually like an endless number of square roots that are nasty decimals that just go on forever randomly or seemingly randomly. I wonder if I have a certain... Yep, I went there. I went there. Okay, I am, again, speaking of cans of worms, I'm not going to open up this can of worms. It doesn't apply to us that much. You don't need to care about this. So all I will say, just so you can kind of not be annoyed and lose sleep over your curiosity, is that this is actually another number in the natural world, kind of like pi. So we use this symbol for like 3.14, 159, whatever. So we use a symbol for pi, which is actually a Greek letter, but we use this to represent pi. We use e to represent this other number that turns out to be irrational. It's called Euler's number, or the natural exponential, if you want to look it up. But you don't need, this is just like another random example. So again, for the most part, when you think of irrational numbers, you're probably going to think of pi and most square roots. It's weird to say most square roots when we're talking about an infinite number of things, but yeah, most square roots are irrational. All right, some quick questions here to kind of, wrinkle your brain a little bit or challenge your brain just about numbers. True or false? The square of a number, so when you square a number, I know we're getting into things like exponents, maybe a little prematurely, but oh well, that's math class for you. You got to be ready for anything. But the square of a number is always greater than the number. Can you think of a moment where you would actually square a number, like raise it to the second power, and it would actually get smaller? Yeah, and so this statement is false. Because if you square 1,
oh, hello.
Hey, what's up?
I am just opening the doors. I've got a contractor who is walking through and assessing the Wi-Fi.
Okay. All right.
This is interesting. What's all the drop-down tops for?
Oh, an escape room game that I made.
Oh, neat.
Yeah.
Yeah, that's kind of cool.
Yeah, it's fun.
Incorporates that curriculum?
No, more like team building for
okay.
like my engineering club mostly. Like,
Oh, neat.
that's how it started anyway. Team building exercise.
Well, that's kind of cool.
Or the soccer team, or whatever I was doing at the time.
Yeah.
All right, so you're gonna leave that open?
Yes, he'll be here in just a moment.
No problem.
They'll just walk through quietly.
All right. All right, back to business. Sorry, I don't know if you caught all of that. About they're doing some Wi-Fi check or something, and I could not think of how to pause the. Well, there it is. Darn it! I could have paused it. I apologize. But anyway, so how about this? When you square 1, it actually just stays the same, so it doesn't get greater. So I guess that counts as like what we call a counter example. And then I was first thinking of like, what if you square a decimal, or what if you square a fraction, right? If you square a fraction, it's not going to get bigger, it's going to get smaller. Don't believe me? Look at your calculator. Next question. True or false? No fractions are whole numbers. Let's read that again. No fractions are whole numbers. Is that true, or can you say that's false? Why is that false? Because of reasons like that. So that's a pretty good counterexample, because this fraction turns out to be a whole number. Next one, true or false? The square root of a number is always less. So if you take the square root of a number, will it always be less? Think about it. That's also false. Can you think of a counter example? Where you take the square root of a number and it automatically makes it go smaller. Because most square roots you might think of like the square root of 16 again. The square root of 16 is 4. That gets smaller, but not the square root of 1, and not the square root of 0, and not the square root of decimals. Okay? So let those sink in. Again, we'll try to keep the video going. Next one, true or false, the square root of a number. Oh, man. Well, here's a hint. I already mentioned this. I already brought this up. Is a square root of a number always irrational? You should know already based on what I said a few minutes ago. That's false because, well, my example, remember, was the square root of 16, but there's an infinite amount of examples. Like here's another one, the square root of 36. That's a nice answer. Can you think of another one? Just one more. Again, there is an endless number of examples you can think of, but can you think of one more? I gave you the square root of 16 is actually nice and rational. Square root of 36. What else? I don't know if this is the one you said, but there's square root of 25, square root of 9, square root of 64, square root of 49, square root of 144, square root of 100, square root of 81. There's a lot of examples even that aren't even that big, but here we go. Moving on. Probably getting to the final stretch here. Again, more vocabulary, more just laying down a foundation of just math skills and really vocabulary again, and symbols and stuff like that. So here's just a real quick basic reminder of inequalities. So this symbol, what is this symbol? A is not equal to B. This is because that's this one. If you have an equal sign, you say A is equal to B. But what is this one? This is actually an equality. These are technically the inequalities. So that's a less than symbol because, again, the way you read it and the fact that, you could think of this as an alligator mouth that is, wants to eat the bigger number. So it wants to eat the B, so the B's bigger, but if you write it like this, you say A is less than B. And so for the similar reasons, this symbol is a greater than symbol. So these next examples, right? They want you to replace right in here, put the proper symbol, whether 2/3 and 6/9 are equal, whether 2/3 is less than 6/9, maybe 2/3 is greater than 6/9. Which one is true? Which symbol would appropriately fit right there? And how could you tell? How could you tell for sure? Maybe you're looking at 6/9 and realizing, wait, doesn't 6/9 literally reduce as a fraction to equal 2/3? Or here's another trick. You can go on your calculator and see what 2 divided by 3 is as a decimal, and also 6 divided by 9 is as a decimal, and realize that they are equal. The decimals are equal, or like I already said, you might have already been able to tell right away that 6/9 reduces to 2/3. So they're the same. How about this one? 4.022 or 4.03. They're obviously not equal. So which one's larger? Hopefully you thought, or you knew, that this one is larger, and so you put a less than. These are obviously also not equal, so which one's bigger? Hopefully you understand that -7 is larger, so we say -7 is greater than -9. And this one, once again, it might help you to literally divide, to get a decimal. So change these to decimals. So I believe, do I have a calculator handy? I'm going to have to use my head. But that's -0.5, and I think this is -0.125 maybe? So which one is larger? Well, this is deeper into negative territory, So this one is smaller. So this is the bigger one. So we put a less than there, okay? There we go. I predicted this correctly, that we would be officially talking about the word opposite when it comes to mathematics. So if two numbers have the same distance from 0 on a number line, they are opposites. So what's the opposite of 8? You know, I hope this fancy, it's not even that fancy, but this fancy textbook definition isn't confusing you at all. What is the opposite of 8? Negative 8. What's the opposite of negative 1? Positive 1. You just change the sign and it makes it fit this definition where it is the same distance from 0 on a number line, just in opposite directions. 8 and negative 8, same distance from 0. Negative 1 and positive 1, same distance from 0. Do you guys remember what this symbol means? What does this say? This says the absolute value of 5 and the absolute value of negative 5. What's the official definition of absolute value? Well, it's right here. The absolute value of a number is its distance from 0. Speaking of distances from 0. So this is the official definition. It's the distance from 0 on a number line. So what is the absolute value of 5? Do you know that it's just 5? Because how far away from 0 is 5 on a number line, right? 1, 2, 3, 4, 5, you know. But what's the absolute value of negative 5? How far away from 0 is negative 5? It's also 5. So whereas this is technically what a textbook would say, okay, I think most people, like myself, honestly, just think of absolute value as something that makes a number positive if it's already positive, it's already positive. But if it's not already positive, absolute value makes it positive. So hopefully all that made sense. So what's left here? Oh, just one more example. That's okay. Guess I'm tossing in this extra example. I don't know if this is actually written on your notes handout. If it's not, actually I can check right now. You have the paper right? No, it's not. So please add this example somewhere at the end of your notes. How would we handle this? Like, what are we taking the absolute value of? Are we taking the absolute value of negative 3, or are we just taking the absolute value of 3 and there's a negative like hanging out in front? Like, what is going on here? Well, the negative is out here. The negative's not in here. So we're just going to take the absolute value of 3, which is, why am I doing that? Just to clarify with color that the negative is out here and the absolute value of 3 is its own separate thing, which is 3, and the negative just drops on down. So this negative is hanging out in front, okay, and then you do the absolute value of 3, which is just 3. So that is the final answer for this example. And then I think I just tossed in like a funny little comic strip which involves pi. So I don't know. But that's it. That's it for the section 1.1.